Imagine I challenge you to explore a vast landscape. As you begin, you run into a problem. Along this landscape, there are valleys of various depth. The deeper they are, the harder it is to climb out and continue exploring. This is similar to exploring an energy landscape for a protein. See, the protein within our cells are never still. They exhibit many shapes, or configurations as we call them, and this helps them perform their various functions. Along our landscape, these configurations are hidden, and the configurations at the bottom of these valleys are those of the lowest energy, and these are more stable structures and usually more important for researchers to find. Microscopy experiments can provide us with a snapshot of the protein, which places us somewhere on this landscape. We then need to run a computer simulation, which applies Newton's laws of motion and structural mechanics to create what's called a trajectory, which is essentially a path. Usually, the longer the simulation, the longer the trajectory and path, and the more configurations we'll find. However, sometimes the simulation gets stuck at the bottom of these valleys, or energy wells, due to the amount of energy required to get back out of them again. This is a problem for the simulation methodology that we typically use, called molecular dynamics, which represents the protein atomistically. This problem is amplified when we look at new emerging techniques in microscopy, such as cryo-electron microscopy, or cryo-EM. Cryo-EM has allowed for larger biomolecules to be imaged, and these larger biomolecules have much vaster energy landscapes and much deeper energy wells. This, coupled with the amount of computing power required to represent these larger biomolecules atomistically, suggests that we should start thinking about different ways of running these simulations. This has inspired fluctuating finite element analysis, otherwise known as FFEA. Whilst molecular dynamics uses particle physics and atomistic representations of biomolecules, FFEA uses continuum physics and represents the surface of these larger biomolecules using a mesh. On the mesh, each face can represent many atoms. It's my project this year to design a pipeline of existing software tools, which may allow researchers to go from cryo-EM data of a biomolecule to a mesh, which can then be used in an FFEA experiment. Using FFEA will flatten the energy landscape of the biomolecule and mean that it's less likely to fall into one of these energy wells. With the horizon of xScale computing appearing, I think that it's really important for FFEA and molecular dynamics to start working together to uncover the secrets behind the functions of these larger biomolecules and life within our very cells.